preparing foundational algorithms. So usually you will not be, you're not going to be asked about anything very technical like recurrent neural networks, transformers. That's not going to happen, but you will probably be asked about linear regression. So how many of you have come up to the first 2 sessions before? Just to get a show of hands. For how many of you is this the first session? Okay, we're going to do a quick recap before we get started. Do you guys have any experience with linear regression? Have you seen it before, roughly? Okay, this was last session, and this is today's session. Okay, we're going to do a quick recap of what we've been doing for the last 2 weeks, to show you some formulas, and today we're going to be covering regression by successive orthogonalization. This is going to give you the same solution as the OLS solution, which we've already seen, but this is better. It's numerically more stable. It's how NumPy, it's how scikit-learn actually implements linear regression. It's not the way in which we do it. So it's very relevant. Of course, if you go on to do an interview one day and they ask you about linear regression, and you mention this, you mention you know this, good points for you. That's amazing. So yeah. Okay, so just to do a quick recap, right? We've got the linear regression model. In linear regression, which is this model here, right? We've got the betas, and we've got the x. X are our inputs. It's why we multiply by the betas. So you can imagine that y is maybe us trying to predict the price of a house, and maybe x1 is how many rooms we have, x2 is the square meters, and so on and so forth. Plus, we always have some error. Our models usually will never be perfect. So in matrix form, which is how we work, and we work this way because for computers it's faster to work in this way, and it's parallelizable or vectorization. You do it like this. You've got a vector y. So the length of this vector is just all of your observations on your data set, right? So maybe it's of size 300,000 because you've observed 300,000 house prices. And then x is a matrix of size rows n, so the observations, and columns p, which is the number of predictors, plus 1 for the intercept, right? And then we've got a vector of errors here. So when we assume this is our model, we talked about minimizing the residual sum of squares. What is this? This is we're looking at the actual prediction in the data set, right? This y. And we take the difference with our prediction. This is what our model gives us. We square it, because that way it gives us a positive number, so we can add errors, they don't cancel out each other. And we try to minimize this expression. And long story short, this can be done by setting the derivative with respect to beta equal to 0, and then you get this solution. Let's look at the yellow one for now, right? This, going back to my first point, it's important to know, I've been asked for this formula a couple of times during interviews. So it's useful. This is the OLS solution. Sometimes we regularize, which means that we impose a penalty on the size of the parameters. As you can see to the error, we can add these here. And this just gives us a more stable solution, because here we have to multiply these 2 matrices and we have to invert them. Sometimes, long story short, if there's multicollinearity, which means that some of the features are related, you can imagine maybe on your data set having the square meters of the house and the square feet of the house. These are going to be very related, which in the world of linear algebra means that this matrix is going to struggle to invert, right? So to make our solutions more numerically stable, we can add this penalty, and then our solution becomes this. Right here, lambda is just this constant, and I is the identity matrix of size p times p. If you're not familiar with this, we upload everything on GitHub. I'll give you the link afterwards, and you can give it a read. Okay, today we are going to do regression by successive orthogonalization. And this is going to give you the same exact solution as OLS. However, this is better. This is how actual libraries implement linear regression. It's faster, it makes your results more interpretable. It's going to help you think about how OLS actually obtains a solution, and what happens when the columns, the inputs, are related to each other, as with the case of square meters and square feet. Right? Does anyone have any questions up until now? No? Amazing. Okay, so the regression, right? We've got y, we're trying to estimate the betas, x is our data, this is the error, so we're trying to estimate this, right? There's just a column vector, from measure beta 0, beta 1, beta 2, all the way up to beta p, because we've got p predictors. Right, I'm just going to give you a series of steps. I'm going to try and make this as clear as possible. So, step 1, we're going to center the data. If you're familiar with normalization, this is going to be very similar, which is for each predictor, we compute the mean of that predictor, we compute the mean of the target, and for each observation, we're going to subtract the mean, and we're going to subtract the target. So, for the houses, you can imagine one column being the number of rooms of each house, right? So we're going to take the mean number of rooms, which maybe it's, I don't know, 4.2, right? And we're going to divide that by each and every single observation. And we're going to do the same for the target, right? So we're going to observe all the prices, and we're going to subtract the mean from these prices. All right. The reason for that is that now our regression model becomes this. And if you don't see any difference, well, this should be BI for starters. There's a wee typo that I made here. But if you don't see any difference, you should, because there's no intercept now. So we don't have to estimate the intercept. We're going to get back to it later, but we're going to first estimate the predictors from all the way from 1 to p. Right? Can anyone see or give me like a rough interpretation as to why you think now we don't have any intercept here when we send it the data? No? Okay. Roughly speaking, the intercept is computed as the mean of your data, right? So if you subtract the mean, then the mean is going to be 0. So the intercept is going to be 0. Very roughly speaking, we can show it mathematically later. Okay, so we're going to go into the core idea of successive orthogonalization. All right. Just before we get into this, does anyone know what two orthogonal vectors are? Yeah.
We did cover that on my math module, but I do not particular. Is that the one which means when you change them they are the same?
Wait, I'll draw it. I think drawing it will be much easier. Okay, so when you have two orthogonal vectors, right, they form a 90-degree angle. Okay, that's it. This is easily seen here, but when you are working with higher dimensional spaces, right, in the third dimension, then this forms another 90-degree angle, and then in the fourth dimension, I don't know, you can try and figure that one out. Yeah, the key idea is that the vectors are going to be orthogonal to each other, which, this is very roughly, by the way, this is not an exhaustive explanation, which means that when we're trying to make a prediction, is very easy to know how each vector affects this prediction, because they're orthogonal to each other. So you go like, okay, so this one affects it this much, and this one affects it this much. This is very roughly what we're doing here. Explain more formally, we say that two vectors are orthogonal if taking the dot product gives you 0. Right? So, once again, if you've got a vector that's x1, x2, all the way up to xn, and you've got another vector of the same size, that's y1, y2, all the way up to yn, their dot product is just x1 multiplied by y1 plus x2 multiplied by y2, all the way there. If this gives you 0, then your vectors are orthogonal. Okay? So we say that all of our vectors, which now we're thinking about the column vectors of our matrix, are orthogonal if all of the possible dot products amongst these vectors give you 0, provided that we're multiplying different vectors. We're not multiplying the same vector. So in mathematical notation, what this is saying is the dot product of this column vector times this product vector for all possible combinations of k and j, given that k and j are different, is going to give us 0. So if that is the case, and only if that is the case, then we can compute the OLS predictors with this formula, which is the dot product of the given column. So once again, you can imagine the column of the rooms in a house, right? So maybe you've got a column that looks like this: house 1, 2 rooms; house 2, 5 rooms; 6 rooms; 1 room. And if you just take the dot product of that with this way, with the prices of the houses, right? Like this could be, I don't know, 200,000, so on and so forth. You take this dot product and you divide it by the dot product of the vector itself. You get the OLS coefficient for that variable. That's it. So what this is saying is that this coefficient is not affected by any of the other variables, only by the column of rooms in this case. Does that make sense? Yeah. So the idea is going to be to transform this matrix that we have and make it so that all vectors are orthogonal to each other. And then once we do this, it's very easy to compute OLS. And given that you've got enough observations, this scales up quite nicely, so it makes your solutions faster. Especially if you compare it to this solution where you have to multiply two matrices, which is a lot of work, but also taking the inverse is a lot of work, right? Like multiply again by matrix. You'll see as we go. All right, so this is the core idea. This is what we're trying to achieve, right? Now into the core algorithm. This is sometimes referred to as the Gram-Schmidt algorithm. And we're going to start like this. All right, remember that this x has this twirly sign because we've centered the data. This was the first step, right? So we're not dealing with an intercept anymore. And we're going to say that our first orthogonal vector is just equal to our first vector in our data. You can think about the number of rooms once again. Right, so this one we're just going to keep the same. Now we're going to do the following algorithm. We're going to compute this coefficient right here. This is a scalar, right? This is dot product here. And we are going to compute z2, we're going to multiply z1, this is the dot product, by the second vector. And we're going to divide it by z1 times z1. And we're going to subtract to z2. We're gonna have the second column vector. And we're going to subtract this coefficient times z1. It's just a formula. We're not going to discuss the intricacies as to why this is the case, because it would take hours. But yeah, this is how it works. Okay, now let's say we want to compute z3, right? So we take the third column. This now can be the square feet of the house, right? All of the observations. And we are going to subtract a13, where all the a, k, j's can be computed like this, right? Times z1 minus a23 times z2, right? So, roughly speaking, the way we compute the vectors is we start with z1, which is our first vector, right? And then, sorry, just going to say equal. And then z2 is going to be equal to x2 minus 1 constant times z1. And then c3 is going to be equal to x3 minus another constant z2 minus another constant z1. And then x4 minus a constant z3, constant z2, constant z1, and so on and so forth, right? So if we are computing, I don't know, the seventh column, we're going to be subtracting 6 different terms. And the way in which we compute those terms is like this. This feels a bit repetitive for us, but when you write a Python loop to do this, it's very, very fast and conceptually very easy. So as you can see, generally speaking, we've got a zj, right? Which is how we are orthogonalize the jth column of our matrix. And this is going to be equal to the original column of our matrix minus A1j z1, where A1j would be just substituting k for 1 and the j for the jth, right? Minus A2j z2, blah, 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 all the way up to A j minus 1j and z j minus 1. So how could you do this in Python? This is the code. Looks much simpler this way, doesn't it? So what you're doing is for j from 1 to p, so for each and every single one of your columns, because you've got p predictors on your linear regression model, we're going to go from k from 1 to j minus 1, right? So for like z3, we had to go from z1 and z2. So 3 is j, and 2 would be j minus 1 here. So we're going to go from k to 1 minus j, from 1 to j minus 1, and we're going to compute the dot product of zk and x j here divided by the dot product of zk, and then which is subtract this to zj, right? When this is only 1, we only subtract it once. When this is 3, we subtract it 2 times, 3 times, and so on and so forth. So now we have a new matrix, matrix that we call Z, right? We started with X, and we've turned X into Z, right? And the columns of this matrix are orthogonal. So the vectors, which you can imagine, it's hard to imagine, but you can imagine one of these vectors, right, as being the square feet of a house, all of the 300,000 observations, and 1 to be the number of rooms. And if you map these vectors into a 300,000 dimensional space, they have a 90-degree angle, right? It's making your head explode right now. Yeah, so this is what's happening. So now, this is our new linear regression model, right? So now we know that our centered y, so this is not our original y, this is centered, is going to be equal to us multiplying our new columns by our parameters, new parameters. So remember that the new parameters are obtained like this, which is what we discussed in step 2, I believe. Right, we can compute the OLS coefficients. The only difference is that these parameters are not equal. They're not equal because now we've got an orthogonal basis, and earlier we had a matrix that was not orthogonal, so there's going to be some differences, but it's very, very easy to go from gamma to beta. Okay, so here you've got some details in matrix form. Our X matrix is related to our Z matrix in this way, where R is this matrix. I'm not going to go in full detail for this, but you can have a look later. And then gamma, this means that gamma is equal to RB, which means that beta is going to be equal to the inverse of this matrix times gamma. In algorithm form, since R is upper triangular, which means that below these ones it's all zeros, we can use this algorithm, which is very fast to retrieve all betas. Right? Now, instead of starting from the start, we're going to start from our last column, right? So from our pth column, and we're going to say that beta p is going to be equal to lambda p. Okay, this is good. And then for the next one, we are going to say that bj is going to be equal to lambda j minus, we're going to do this sum, rjkth, where the rjkth element is on this table, times beta k. And we're going to subtract this all the way from j plus 1 all the way to p. Right? So how do you think about it? If you've got beta 4, right, and we're trying to estimate beta 4, and maybe we say that there's 5 predictors, this is going to be equal to lambda 4 minus some constant times beta 5. And then for beta 3, this is going to be equal to lambda 3 minus some constant beta 4 minus some constant beta 5, right? and the parameters in this case, they're given to you by this matrix here. And remember that the A12, A23, A13, these are given to you from this formula here, right? So you only have to follow the formulas, really. So this is how you obtain the betas, and now we have to get the intercept back. Remember that from the start we just ignored that there was an intercept. This can be done with this formula, very simple, just equal to the mean of y minus just multiplying all these beta j's times the mean of x. And that's it, we got the intercept back. And these are the original means from the data, by the way. Okay, does anyone have any questions before I discuss why this is the case? I know maybe I was going a bit fast, but...
Well, I got one precise one that fortunately I do understand. This transformation from normal matrix to orthogonal one and then back, will we not like lose some sort of data? Because we, as you said, we need to try to find our actual beta parameters. We trying to converge them through the theta parameters that we found from orthogonal. But doesn't mean that because it's orthogonal, it's literally different metrics, and we lose some potential info that could be used.
No, we lose no data. The betas are mathematically exactly the same as the OLS solution. The reason for that is that in reality everything we're doing is just this transformation here. Just multiplying by a matrix. The matrix is invertible, so you can retrieve it. But the important thing here is that R is upper triangular. This in matrix form sometimes is referred to as QR decomposition, which everything it means is we've got an upper triangular matrix, so we can obtain or we can retrieve having the inverse of this matrix by using this simple algorithm instead of actually computing the matrix. So it's numerically more stable as well. But yeah, no, it's the exact same. When you try it on the exercises, you'll see that it's slightly different, like ever so slightly, just because the way in which computers do float numbers and multiply and whatnot. But you'll see it's pretty much the exact same. So yeah, I've been explaining this for a bit, but yeah, one of the questions, why bother doing this? It's numerically more stable. We don't have to multiply to matrices, so we're working with smaller numbers as well. We don't have to take the inverse directly of a matrix, which can be numerically unstable. And it's a standard method in many numerical libraries. Also, and this is an important point, it gives us a way of thinking about OLS. And it gives us an intuition as to how OLS computes its parameters, which is completely invisible if you're only explaining OLS. And it's the following. So when we're computing our beta parameters, right here, you'll see that we are what we are doing is roughly the following. I'm just going to give you this example, right? We are observing x3, which is one of our columns, and this column maybe was the number of the number of rooms, right? And what we're saying is, if we offset maybe the prediction value of the size of the house, which could be z1, right? And then if we offset the value of maybe the neighborhood of where we live in, which could be z2, right? How much does x3 explain? How much does x3 help us explain the price of the house, right? So we are basically eliminating the effect of the neighborhood and the number of rooms completely, and we're using it to say, okay, once we eliminate this, how useful is this variable actually, right? As I said, when you compute the beta parameters with this way, it's exactly the same as doing OLS, which means that if you've got a predictor, right? Imagine you've got two predictors, beta 1 and beta 2, right? And just to give you this example, I'm going to give you two predictors that are very correlated. So one would be the square meters of a house, and one would be the square feet, right? What we're doing with OLS is we are first ignoring beta 2 and we're saying, okay, how much of the effect or how much of the price in the house, right, is estimated by beta 1. And we say, okay, we say maybe this much is it's times 12. So if you maybe times 700, right? So if you multiply the square meters of a house times 700, you roughly get the value of a house. But then we go into square feet, and we're trying to estimate beta 2. But the thing is, square meters already explains a lot of what happens with square feet, right? It's practically done all the job it had to do for square feet. So here we're going to get a meaningless parameter. We're going to get like 2, right? Because these two variables are very correlated. So then your boss is going to ask you, okay, so how much does square feet affect the price? And you're going to say times 2, and he's going to look at you and say that doesn't make any sense, right? And it doesn't, because the inputs are very highly correlated. So this is what this method teaches you. It teaches you that the order in which you compute the parameters matters, because you're computing one after the other, effectively. This effect is invisible when you do it with OLS, but it is visible when you do it in this way. So also along the way, there's some easier ways of detecting when two variables are highly correlated, but that will be in the exercises. Okay.
I got a question.
Yeah.
So by calculating Z, like, okay, when we're calculating Z3, we discarding Z1, Z2, that's what you explained. So when because you explained it first, I was not sure when we use it actually to find the parameters, because that's at the end what we're trying to do. We are using a couple of Z's, which is a couple of matrices, or we're using the last one, which is kind of strange because the last one is just the last parameter from your point of view.
Yeah, but that was to compute from gamma all the way to beta.
So we use all material, all Z's as we need.
Yeah, but the important thing where all the information is passed is here, and this is where most of it comes from. So it will go from left to right, roughly. But you're going to be able to implement it, so you'll see it once you do it. So these are the exercises I've prepared for the people that haven't come before. So you know, this is our GitHub, right? Are you guys comfortable with GitHub? Have you used it before? Yeah, Rob? Or you can ask ChatGPT, it's fine. Okay, so it's called, if you look up Queen Mary Machine Learning Society, QMML, you're going to find it. I think it's also on the description of the WhatsApp group chat, also on the QMSU website, so there's lots of places where you can find it. And right now we're doing machine learning. As you can see, I've just uploaded session 3, this is what you can see here, and this is what we did today. Here you've got the notes of the sessions, and I upload them in a bit of a silly way, which is I just put them by order, right? So this, even though this is session 3, this is the first session, and then this is the second session, and then this is today's session. That way, if you want to download them, you got them all together in a single document, which is useful. And here, I think I've got it on VS Code here, yeah, that'll be easier. And you've got the session folders here. Let me zoom in a little bit, right? And here for session 3, you've got the exercises, right? So this is just me loading some data sets so that you can play with them. So I've done the dirty work for you. You don't have to worry about them. These are going to be the exercises, which they are pretty much what we've done today, just step by step, so that you can actually code it yourself. That's why I also include some pseudocode. But yeah, first you're going to have to implement functions to center a vector and then center the columns of a matrix, right? So we're just looking at the columns, we're calculating the mean, and we are subtracting it from each one of the observations. Then you're going to implement the Gram-Schmidt algorithm. So you're going to give it the matrix X, and you're going to have to output the matrix Z and the matrix R, right? and then you can verify that your algorithm works. If the way in which you verify it is if Z times R gives you roughly the matrix X, it works, amazing, you're doing great. Then you're going to compute the gamma coefficients. Based on that, you obtain the beta coefficient, and based on all of that, now you can create a function that's your OLS via orthogonalization function, and you can compare your results that you obtain with OLS, right? So here, if you if you go to the exercises, you'll see I've just created placeholder functions here for you. One thing that I do recommend, because I assume that most of you are, I mean, since you're here, right, like no one's creating you, most of you are here because you either want to prepare interviews in the future or because you're really concerned or motivated by learning. So what I do recommend when you practice these exercises is that you do not use LLMs to give you the solution, right? You can use them to explain some notation to you, right? Like, I want to multiply two matrices, how do I do that? And then the LLM is going to teach you how to do it, and then now you've got a new tool on your skill set, which is how to multiply two matrices. I think if you start learning this way, rather than just having it give you the full solution, it's going to be much better for you in the future. And not only that, now you're going to try doing this for the first time, assuming you are, and it will take you some time to get it working the first time. Once you get it working, try doing it again, right? Try doing it again, and maybe the fourth time try doing it without looking up anywhere. This is how you learn. It's a lot of this is just repetition, right? When you see someone just like coding very fluently and you're like, oh, I want to be like that, they've just repeated the same thing over and over again. So this is how I recommend that you approach these exercises. For the people that haven't come here yet, we've got session 1 and session 2. You could do this session without having done session 1 or session 2, just because it's a different method, right? But if you want to give session 1 and session 2 a look, here they are with all the notes and some exercises as well. And just to finish, for the people that don't know it yet, we do have certificates of engagement that we give from the society. These certificates you can put on your CV, you can put on your LinkedIn. We're working on them, but they're going to be given to the people that do complete these exercises. So the next session is going to be the last linear regression session, and then you're going to have roughly 2 or 3 weeks to work on them. And if you complete them, you get a certificate of engagement, and whoever does the best submission, they get the best submission certificate. So yeah, it's a little something if you're motivated by that. But yeah, so yeah, that should be everything. Does anyone have any questions? No? All right, thank you.